Is it start recording? Okay. Right. Good morning, 3A03. Okay. So today we're going to continue with this problem. Right. So it's a continuation. So just slightly recap where I did stop yesterday is to calculate the stress state. Okay. So I've just listed down the formula. Before I go on, we are trying to analyze, okay, the stresses acting on this shaft, and we're going to specify what is the minimum diameter given the strength of the material that we are taking, that we have is 100 ksi, and in shear is 50 ksi. Okay, so why I'm doing this example, I want to give you a snapshot of what you will be learning throughout the whole 12 weeks. And at the end of the day, what will your outcome be? Okay, because I want to make a very clear distinct that this is not the same like your previous courses. Okay, so as you can see, the loading situation is very simple, right? You have an axial load, you have a bending moment, and you have a torque. So now I'm going to again repeat drawing my transformation. Okay, so this is my transformation. So with this transformation, right, we are able to identify what is our stress, our loading condition. Okay, so we know that 2,500 is axial, 2,300 pounds feet is your torque, 1,500 is your bending moment, and I will teach you guys how to identify what is a bending moment, what's a torque. I did that very briefly yesterday. Okay, is very brief what I did yesterday. So now the formula to use is real straightforward. Not straightforward, but you guys have seen it before. It's nothing new for now. Okay, you have seen it before, right? So you have axial load, which is px over a, and then contribution by bending moment. So remember, in the real world, the loading condition is not 2D. Okay, it's going to be 3D. Right? So for this case, what you can see is the axial load is in X. You have two bending moment, one in Y, about the Y-axis, one about the Z-axis. Okay, so it's a 3D state loading. Then the torque, okay, you will see the formula in the torque where you have T. So in fact, this T over here, I'm going to erase this. This is torque in the X direction, R over J. So that's the torque. You guys have learned torque before, okay, in 2PO4. But you guys have not touched on how shear force will affect the shear stress, which is given the formula over there, which I will teach in week 3 and week 4. So that's where I stopped yesterday. So the next thing is we are going to identify the region of the highest, right, stress state. Okay, so remember, if you are given a shaft like this, okay, I mean, for this case, it's simple. The problem say calculate that region. Okay, but you don't always do that. Okay, you only will calculate where the stresses are the highest. Okay, so we are going to go into failure analysis. Okay, we are going to go look into failure analysis to determine at what region. Okay, at what in which region in the cross section where you have where you have where the stresses that you're going to anticipate that is going to be the highest. Okay, so now let me tell you, or let me draw you the trend of the formula that you can see up here. Okay, let me draw you the trend on the formula you can see up there. So I'm going to draw the trend now. Okay, So now, if we have our circle, yeah, I'm going to draw our cross section. Okay, so this is our cross section. I'm going to draw it big. Okay, so this is a cross section of our shaft, right? And if I were to follow the transformation, this will be our Y, and this will be our Z. Okay, so that's our transformation. So now I'm going to sketch what each equation mean. Okay, I'm going to sketch now. All right. So this is our x-axis. So our x-axis, it can be normal stress or it can be shear stress. Okay, and then we have our y-axis. Right. So this is our y position, and this is our 0. So at this line where it's 0, okay, is basically we are at our centroid. Okay. Now I like to call this centroid and not neutral axis, is because not always the centroid is equal to the neutral axis. Sometimes it is, but a lot of times it's not. Okay, so let's look at how. So what I'm trying to draw down here, right, is the stress distribution profile. Okay, so the first one I'm going to deal with, I'm going to move this so you can see the formula also. Okay, so we are going to look at P over A first. Okay, let me move this slightly so we can see better. Okay, we are going to look at P over A. Now, P over A is so straightforward. Okay, it is constant throughout the cross section. It's an average stress. So I'm going to draw the first distribution. Okay, I'm going to draw if I can find my cursor. So the first distribution, I'm going to assume it to be compression, right? So so this is the first distribution. I wonder, is there a different in color? Yes, there's a different in color. So this is the first distribution. And this distribution over here is equal to P over A, right? It's constant. There's no effect on the radius of the shaft at all. Okay.
Could you
So
slow down a bit?
yes, sorry, I realized that. Let me bring this to like 200. No, 200 is too small for you guys. Let me do this at 250. Okay, better now. Okay.
Thank you.
So that is your P over A. Then your next equation, which is your bending moment equation, can you tell me how will your bending moment distribute? Anyone? Anyone? Can you tell me how you will distribute? What will happen at the centroid for the bending moment? Anyone, please? Regarding normal stress. It's equal to 0. Well done, okay? So the next distribution will look like this, okay? The next distribution will look like this. So you go to 0. Right? Hopefully you can see that. How come it's not refreshing? Hold on. Right? So that's a this distribution. Excuse me. So this distribution is due to the bending moment. Okay. So this is stress X. And this distribution is due to stress X is equal to my over I. I just wrote down the formula. Okay. Now, the next one is the torque, right? How will the torque distribute? Anyone? How will the shear stress TR over J distribute? Can anyone make a guess, please? How does it look like? It's difficult to describe, right? I can totally understand. So how it will look like this. Okay. Oh, sorry. I think I overshot the curve, but it's okay. So you look like this. So you come down here. At the center where the radius is 0, okay, and then from here, all right, you go maximum on the surface again. Okay, because the formula over here now, this is shear stress. Right, shear stress is equal to TR over J. Then finally, what we have is the last one is the one caused by the shearing force. So at the shearing force, this is the one that is causing a lot of problem. By the way, I'll tell you why. Okay. So the shear force inducing the shear stress will look like this. Right. Okay. Good morning. Why is VQI over IT causing the most issue when compared to MY over I or TR over J? Anyone? Hello? You guys there?
Because it's max at 0.
Hallelujah. There you go. The problem is this, okay? For this case, the maximum is located at the where? Centroid. Right? Or I'll say this, okay? Centroid is at its maximum. For the other two cases, the centroid, okay, the centroid, at the centroid, okay, at the centroid, is equal to what? 0. I don't write 0 like that. Wait, you guys are wondering. It's at 0. And then the other one, the one caused by bending moment, okay, at the centroid, is also equal to what? 0. Okay, where px is equal to p over a is a constant. So down here, this one at the centroid or away from centroid, right? It does not matter. Okay, that is constant, right? So now the question asked is this, we cannot isolate all our calculation. We have to, as the term I always use again, we have to what? Integrate. Okay, we have to integrate all our analysis into one. Okay, so now we are going to position different elements in different position now. Okay, so we are going to designate elements at different location for the shaft now. So based on this transformation, okay, and based on this diagram that we have, I'll copy the diagram so you can see better. Right, I'm going to move the diagram. Okay, so you can see the diagram down here now, right? So we're going to position elements on this diagram. Okay, so I'm going to so we are going to have I wonder, can you see this? Okay, so I'm going to put over here elements. Can you see the elements I'm drawing? Yes or no?
Yeah, we can see them.
Yep. So these are all the elements I'm going to position on the shaft. Okay. So elements are, you can say these elements are like strain gauges. Okay, I'm going to position the strain gauges there. So this one I'll call element A, element B, element C, element D. Okay, so back onto this diagram over here. All right, back onto this diagram over here. So if I'm going to, okay, so this is element